All right, so today we are going to learn about chemical kinetics. This is actually a really fun chapter. It's one of my favorites. Chemical kinetics are how fast reactions proceed. When you think about kinetics, you should think about how fast something's happening. So chemical kinetics, how fast reactions are occurring. We will start with section 12.1 and just learn about what do we mean when we say reaction rates. So a reaction rate is the change in a reactant concentration over the change in time. Now recall that these brackets here just mean concentration. So a reaction rate is the change in the reactant concentration over the change in time when we do an experiment where we measure the concentration over time for a certain reactant, and then we look at the change in the concentration over the change in time. I think I've said that 5 times now. All right. How do we measure reaction rates? How are these things measured? Well, we run an experiment. So I'm going to show you an experiment in a moment for the reaction of H2 plus I2 makes 2HI. So somebody runs an experiment and we look at concentration versus time data. So the blue line here is our hydroiodic acid, and the red line represents the concentration of both H2 and I2. Notice the H2 and the I2 are decreasing over time because they're reactants. Reactants go down. The product, on the other hand, is increasing over time because products are produced. The other thing you might notice, this curve it's showing it, that the slope for the H2 and the I2 is not as large as, well, the absolute value of the slope for the change in, for the concentration of H2 and I2 is not as large as the absolute value of the slope for the concentration of HI. That's because HI has a coefficient of 2, so it's being produced twice as fast as H2 and I2 are being used. Okay, so we do an experiment and we see how the concentration of reactants and products change with respect to time. And this is how we get rates. The rate at any point in time is the slope of the line tangent to the curve at a specific time for a chemical whose coefficient is 1. So for this class, anyway, we're going to talk about reaction rates being based on anything in the reaction with a coefficient of 1. So for this reaction, we would base the rate on H2 or I2. Or if we only have information about HI, we could just divide by 2 to make the coefficient 1. All right. So let's look back here. So I'm just repeating what I wrote a moment ago, that the instantaneous rate of reaction is based on a chemical with a coefficient of 1. That's very important. So we look at a slope for the chemical whose coefficient is 1. So right here we have a slope. We take the tangent line at this time right here. We take that tangent line, we calculate the slope of the tangent line, and that slope is the actual rate. Now, when we are looking at rates, we want a positive rate. So now let's just look at this real quick. Remember, slope is the change in x over the change in y, which would be delta H2 concentration over delta T. Right here, the change in H2 over the change in time. And note, I put a little negative sign here. This negative sign is because we want, when we look at reaction rates, we talk about reaction rates being positive. Reactants are being used up. So the slope will be negative for reactants And this slope will be positive for products. Oops. Okay. So a reaction rate would be the change in the concentration over the change in time for anything with a coefficient of 1. For reactants, we have to put a negative sign in front because reactant goes down over time, so the slope would be negative. If our coefficient is not 1, we put 1 over the coefficient in front of the change in concentration over the change in time. This might seem a little confusing. We're not going to spend a lot of time on this part of reaction rates. More important is, how do we use experimental data to actually find what's called a rate law? So, rate laws. Okay, section 12.2. What is a rate law? Rate laws are equations that tell you how quickly a reaction is happening. It's a mathematical equation that gives you an idea of what's happening in a reaction and how fast it's going. And a rate law looks like this, right here. And we do not, well, one thing that students often do, we do not write rate law equals. Do not write rate law equals. This whole equation here is a rate law. But the rate law is that the rate is equal to, now what are all these variables? Let's define all these variables. A rate equals K, the specific rate constant, times the concentration of each reactant raised to a power. Now, so A, B, and C are just reactants. They cannot be products. They can be catalysts. X, Y, and Z, these exponents right here, those are called the order of reaction with respect to a specific reactant. And these orders are only determined experimentally. And for some reason, I'm having trouble. Hold on. Sorry, I was having trouble moving the screen up and down. I don't know why, but we're back. Okay, where were we? Oh, we determine K, X, Y, and Z with an experiment. You have to be given experimental data or do an experiment, and that's how we determine the exponents and K, the specific rate constant. And one more definition here. There's something called the overall order of reaction. And for the overall order of reaction, we just add up the exponents, x plus y plus z. Now, what is this order of reaction with respect to a reactant mean? We will learn at the end of the chapter, when we learn about mechanisms, what these orders represent. And just a real quick thing, you don't need to know this yet, but students often get frustrated because they're like, well, what is this? I want to know what it means. So just real quick, you'll learn it later. The order of the reaction with respect to a reactant represents how many of each reactant are present in the activated state, the activation complex for a reaction. And we're really getting ahead of ourselves right now, but we have mechanisms for reactions, and in these mechanisms we have activated complexes, and the order represents what chemicals are present in that activated complex that's going to create our final products and allow the reaction to proceed forward. Again, don't worry about that for now. That comes up later, but for those of you who like to have sort of some better understanding and want to know what the order is, there you go. Okay, so let's do an example. We have this reaction, and we find by experimental data that we get this given rate law. And I want to know, what is the order of the reaction with respect to O2 and N2, and what is the overall order of reaction? You might want to pause now because I'm going to show the answer in a moment. Pause. Okay, so the idea of the pausing was that you should be figuring it out on your own. So if you haven't paused yet, go ahead and pause. Okay, here are the answers, so pause before I show them. Okay, here we go. So the reaction is second order in oxygen. It's first order in N2, because even though I didn't write a 1, there really is a 1 there. And overall, we just add the 2 plus the 1, so the overall order is third. And hopefully you got that. Okay. Moving on. Section 12.3. How do we get a rate law? How do we get one? That's section 12.3, determining a rate law. And in order to determine a rate law, you have to be given experimental data. Or if you're a researcher and you want to determine the experimental rate law, you actually run a bunch of experiments. And this is the kind of data you get. You run a series of experiments. So there's 1, 2, 3, 4 experiments here. And in each experiment, you keep the concentration of all but one reactant constant. Just notice this is backwards. Okay, we keep the concentration of all but one reactant constant, and we measure the rate of the reaction. Let's go back and look at what does that mean? How do we do that? We use this kind of information right here. Okay, so this experiment is run, and then we get an instantaneous rate at a certain, whoa, didn't mean to move that. We get a rate at a certain time. We get the slope. I didn't do that slope very well. We get the slope of the line tangent to the curve, and we get a rate of reaction. And then we do several experiments. We actually do the initial rate right here. So we would base it right at the beginning, based on the initial concentrations of our chemicals. So let's pretend I didn't do this over here, because we need to know the initial concentration, and we look at the initial rates. So let's go back to our problem. So you run a bunch of those experiments. You look at the initial rate of reaction, because you know your initial concentrations of each chemical. So what do we do with this data? We get the data, and there's a procedure here. You have to find 2 experiments where the concentrations of all but one reactant are constant. Then you plug the experimental values into the rate law of one experiment divided by the rate law of the other experiment. And then you solve for the exponent that can be determined. Let me show you what that means. It looks a little odd. Okay, so let's find 2 experiments. Let's erase this first, where the concentrations of all but one chemical are constant. And I see run 1 and run 2. These are constant. So I can do this. And I tend to like to put the rate that was larger. Notice this, we're going to look at the initial rates here. The initial rate in run 2 is larger than the initial rate in run 1. So I'm going to put experiment 2, or run 2, on top. So rate 2 over rate 1. And we know the rate is, hold on, let me erase this for a moment. We know the rate is K NO to the X, NO2 to the Y, O2 to the Z. We know that. That's just any reaction. You just write rate equals K, and then you put each reaction raised to a power. It doesn't matter if you use X, Y, and Z or A, B, C. It's up to you. So we're going to do rate 2 over rate 1. It's a 2. And let's look at what that looks like. So we need to do rate 2. Rate 2 is right here. 4.2 times 10 to the minus 2 over rate 1. 2.1 times 10 to the minus 2. That was right here. Rate 2 over rate 1. Now I'll plug in K, and I have to put in my concentrations. So I'm looking at experiment 2, and I need the concentration of NO. Let's see, where's NO? In experiment 2, right here. 0.20 molar. I'm not going to put in the units to the X. Now I need NO2, which is right here. 0.1 to the Y. And I need O2. 0.1 to the z over experiment 1, or run 1. So again, I start with my NO, 0.1 to the x, 0.1 to the y, and now I do the O2 right here, 0.1 to the z. Hopefully you can see some things cancel out here. It works out very beautifully. The 0.1s cancel, the 0.1s cancel, because I had 0.1 to the y over 0.1 to the y, that cancels out. 0.1 to the z over 0.1 to the z, that cancels out. And the k's cancel. All right, left side. This is just equal to 2. 2 is equal to, now I can simplify this. I can bring these together because they were both raised to the x. And that is 2 to the x. So I now know x is 1. How beautiful. Okay. I think you should pause and try to do the other two. And I will go through how to do it right now. But go ahead and pause if you want to figure it out on your own. I will show you how to get the y and the z exponents. So, for those of you who are not pausing, just keep watching. For those of you who are pausing, you should pause because you don't want to watch this part. Okay, so I need to find where another chemical, two chemicals are constant. I'm not seeing anywhere two chemicals are constant. Found it. 1 and 4. Okay, sorry about that. So in 1 and 4, the NO is constant and the NO2 is constant. And I'm going to notice the rates are the same, so it doesn't actually matter which one I put on top. So I'm just going to pick to do rate 4 over rate 1. So rate 4 is 2.1 times 10 to the minus 2. Rate 1 is also 2.1 times 10 to the minus 2. 2.1 times 10 to the minus 2 over 2.1 times 10 to the minus 2. I'm going to have to do the K, and I'm going to plug in all my concentrations now. So I will do 0.1, 0.1, 0.2, 0.1, 0.1, 0.1. 0.1 to the x, 0.1 to the y, 0.2 to the z, and it was that right? Let's check again. Rate 2, 0.1, 0.1, 0.2, and rate 1 would be 0.1, 0.1, 0.1. Yes. Okay. 0.1 to the x, 0.1 to the y, 0.1 to the z. Now I check and see what can I cancel. Okay, k's cancel. 0.1 to the x and 0.1 to the x cancel. 0.1 to the y, 0.1 to the y cancels. So I get 1 equals 0.2 over 0.1 to the z, which is 2 to the z. And I say 2 raised to what power equals 1? All right, hopefully you remember this. Z must equal 0. Anything raised to the 0 power is 1. Okay. Oh my goodness. Now, for the last one, we found, let's see, what did we find? We found z and we found x. We need to find y. So it turns out, I don't think there's two more where something is constant. There aren't. So you might have gotten stuck and you're probably watching the video right now. So we don't have one where there are two chemicals constant, but NO2 is changing. However, we know x at this point, and we know z, and we're only missing y. So at this point, we can actually pick any two experiments where NO2 is changing. So I could pick 3 and 4, or actually, I don't want to pick 2 and 3 because I need x to change. Not x. I need the NO to be changing. So I'm not going to pick 2 and 3. So I need NO2 to be changing. Oh, actually, I could have NO constant because this right here is raised to the 0 power. So actually any two experiments where the NO2 is changing would be fine. I'm going to do it the more complicated way just so that you see what would happen if this didn't work out so simply. So I'm going to pick 3 and 4. You could pick 3 and 2 or 3 and 1 or 3 and 4. Okay, I'm going to note that run 4 has a bigger rate than run 1. So we're going to do rate 4 over rate 1. And rate 4 over rate 1, 2.1 times 10 to the minus 2 over 1.26 times 10 to the minus, what was that? 1 equals k. Okay, now I've got, oops, 4 over 1. No, I'm doing 4 over 3. I'm sorry, rate 4 over rate 3. 4 over 3. So 4 is 0.1, 0.1, 0.2. 0.1 to the x, 0.1 to the y, 0.2 to the z, over rate 3. Rate 3, I have to put in my concentrations, 0.2, 0.3, 0.2. 0.2 to the x, 0.3 to the y. What's that? I forgot. Sorry, 0.2, 0.2. Sorry, 0.2, 0.3, 0.2. 0.2, 0.3, 0.2 to the z. I was just plugging in the concentrations. Well, I know x, so I can plug that in also. Right here, I found out x was 1, so I can put a little 1 here and a 1 here. And I know z. Z is 0, 0, 0. Okay, I'm going to simplify this now. And I did that upside down. I said that, why is that showing up? Okay, I said that this number was bigger than this number. It's not, and you can do this either way. Again, it's okay to have it the way I've set it up here. But now I have to actually use my calculator. Okay, I put that in my calculator. Now, the k's cancel, and 0.2 to the 0 is just 1. 0.2 to the 0 is 1, and those would have canceled anyway. Now I have 0.1 over 0.2 times 0.1 over 0.3 to the y. Okay, 0.1 over 0.2 is just 1/2, so I have 0.1667 times 2, I'm just multiplying both sides by 2, is 1/3 to the y. Okay, I got 0.333 is 1/3 to the y. Now, you might recognize that 0.333 is actually 1/3. Or if you want, you can flip this over to get 3 equals 3 to the y. If you flip both sides, or recognizing that this number is actually 1/3. So y must be 1. All right, so our rate is k. Let's go back. Look at the orders. It goes NO, NO2, O2. NO to the x, NO2 to the y, O2 to the z. And there is our rate law. Okay, solving for k, you just plug in a value, but this video has gone long enough. So we're going to work on solving for k in class tomorrow. But our rate law is right here. Okay.